Good afternoon, everybody. Good afternoon. Thank you for coming to our program this afternoon. My name is Haley Blake. I'm the education coordinator here, and I'm going to turn it over to our executive director, Julia Gray, who's working from home. She's visiting from afar. Hi, Julia. And she's going to do the official welcome and introduction of Neil, and then we'll turn it over to Neil for our awesome presentation this afternoon. All right. Thank you. Take it away, Julia.
Great. Welcome everyone to the Wilson Museum, whether you're joining us in person or virtually. I'm Julia Gray, Executive Director here. And this afternoon, I'm joining you virtually from my home in Orland, in the homeland of the Penobscot Nation and their Wabanaki relations. We are so excited today for today's opportunity to travel far back in time with Dr. Neil Comins, Professor of Physics at the University of Maine. Neil is an astronomer, astrophysicist on the faculty of the University of Maine, where he's taught since 1978. He's the author of 21 published astronomy trade and textbooks, and his research topics include, and I'm listing these from his webpage because I don't know what all of these mean. He does science education research, galactic formation, structure, and stability, evolution, stellar stability, observational astronomy, computational astrophysics, and general relativity. Now, a little bit of cruising around online will quickly tell you that Dr. Comins does a wonderful job of presenting complicated topics like this to students and the general public, so we're excited about that. Visitors to the Wilson Museum will find exhibits take you back some 540 million years or so to the Precambrian era, as early life was evolving on Earth. This afternoon, Dr. Comins is going to take us back something like 4.5 billion years to explore the formation of our solar system and how that set the stage for what happened in the Precambrian. Special thanks to Bangor Savings Bank for sponsoring this program, which is part of our Connecting to Collections program series. And welcome, Dr. Comins.
Well, thank you very much. It is a pleasure to be here, and I'm going to try to share a screen and get things going. I want to make sure it was crystal clear. She said that I have been teaching at the University of Maine since 1978, not 1878. just to be sure. Okay. So let me begin. If you look around, I mean, we live in an environment with matter, particles, everything is made of stuff. And there's radiation, like the light, the radio waves, and so on. Okay. And I invite you to just choose something, anything that you can hold on to as a physical entity as we go through this, because as you will see, it wasn't there, and it took a long time to get to the point where the microphone existed, paper existed, whatever. So we're going to go for a big stroll here. In the beginning, okay, there was an event. We scientists call it the Big Bang. The truth is, science has no explanation for why the universe began, period. We don't yet, okay? Having said that, we now do have equations and theories and calculations that explain virtually everything, not completely in detail, or I'd be out of a job, but all the stages we now have explanations for. From a time of, you ready for this? 10 to the minus 43 seconds, and roughly a millionth of a billionth of a billionth of a billionth of a billionth of a second after the universe began, science comes into the game. And so that's what I'm going to be talking about. Now, when the universe began, 13.7-ish billion years ago, okay, there was no matter, there was no energy, nothing that we take for granted existed at all. So those things had to come into play, and they did it in stages, and that's what I'm going to explore, the stages at which things came into existence. Okay. First of all, the explosion, the Big Bang. All right. The universe, when it first formed, was literally an explosion. It grew and grew and grew. And if you want to know, let me answer the question that may be on your minds. It is not, the universe is not moving into something else. The universe is creating space and time as it expands. So that process is carrying on today. The universe is getting bigger. And we see that with our technology, with our telescopes. Okay, that event, the Big Bang, was an extremely hot event. And we know that today because we know the temperature of literally the temperature of the universe today. And then the universe is expanding, and therefore we can run backwards in time and calculate what happened as the universe was smaller and smaller and smaller. Well, what happens when you take the environment of the universe today and compress it down to a really tiny volume? Gets hot, gets really hot. And the temperature, as you can see here, when at 10 to the minus 43 seconds after the universe began, its temperature was 10 to the 32 degrees. Room temperature today in the same units, Kelvin, is about 300. So it has obviously cooled off tremendously and continues to cool off even as we speak. Okay, so one or two technical, it's not too busy. So let me just take you through this diagram here. The horizontal axis is time, okay? And the vertical axis is size. So the universe, beginning in the lower left, was a very tiny object. And when the universe began, it was created in an unstable condition. And let me give you an example of that. Suppose you have, if you've ever been to New York City, the Empire State Building, okay? It's a really tall building. And suppose you had a marble and you put it on outside windowsill of the Empire State Building and just let it sit there, okay? Well, the vibrations of the city, the planes flying overhead, all this kinds of stuff, going to make the marble wobble. It's going to become unstable. And it will eventually start rolling to the edge and fall off. Okay? In the same sense, the universe was created in a condition that it had to readjust. The marble falls down to the ground. The universe, at that time, 10 to the minus 35 seconds after it began, underwent a huge readjustment. It became much, much greater. You can see 50 orders of magnitude larger in a fraction of a second. So the universe was unstable when it formed. It stabilized itself by expanding dramatically in a tiny fraction of a second. And during this time, still no matter, no energy as we know them. This was a universe filled with an energy that there was just one kind of energy at the beginning of the universe. Okay. And since that day, the universe has continued to grow, but more slowly. And we, with our technology, can see the universe growing. So we know that that is in fact the case. Okay, the other thing I want to take you through here is the formation of matter and energy. And this diagram shows the development of the concepts of energy. There are at least 4 kinds of energy in the known universe. Okay, gravity, electromagnetism, light and radio waves, and then 2 kinds of energy that act to hold atoms together. Okay, and when the universe began, they were not there. It was just a one kind of energy. And over the time from 10 to the minus 43 seconds until about a trillionth of a second after the universe began, that changed. The first of the 4 energies that became real was gravity. gravity is, is holding us down to the earth, among many other things. And as the universe expanded, the temperature was dropping. You can see the temperature on the top dropped 100,000 degrees in a tiny, tiny fraction of a second. And the next energy that became real is called the strong force. It helps glue the particles we call protons and neutrons together. So it's absolutely essential. And then eventually, after only a trillionth of a second, the other two forces, electromagnetism and the weak force, also which works at particle level, separated. So there are four forces in nature, and they came into existence. And we still don't have the matter here yet. It's coming right up. But those are the energies that we know and love. I mean, electromagnetic force includes things like heat, keeps us warm, among many other things. Okay, the temperature today, the universe was really hot back in the day, 10 to the 32 degrees. The temperature today, which has been measured, by the way, is about 2.7 degrees Kelvin. The room temperature, 300 degrees Kelvin. Okay, but the overall universe has a temperature, and it is expanding and cooling down even as we speak. Okay, so let me take you through the first 3 minutes of the life of the universe. We just, obviously, in the first fraction of a second, we got the four energies. Now we need the particles that we're made of. Okay, and the particles that we're made of came into existence in stages. In other words, when the first particles came into existence, it wasn't the protons and neutrons and electrons were made of. The first particles in the universe were things called quarks, which I'll show you what they are in one sec. Electrons, that's what flowing through the power lines creates electricity, and neutrinos. I'll talk about them later, but let me just say that neutrinos are created when the fusion of atoms, coupling them together, occurs. Neutrinos are created. And well, I'll give you the punchline to that story. The sun is fusing energy. You might have heard the Lawrence Livermore Lab in the news a couple of days ago announced that it has created a fusion condition where it fuses particles together and they stick and give off energy, and it gives off more energy than it took to make the fusion. Okay, that's a huge thing. It's called controlled thermonuclear fusion. And when that occurs, a neutrino is created. The sun is doing that in huge, unbelievably large numbers of events per second. And so what about that? The sun's fusion creates neutrinos, these particles. And there are over 1 billion neutrinos passing through your body every second from the sun. Do they interact with the body? Incredibly rarely, which is a good thing, obviously, with 1 billion of them passing through. But the point is that they were created at the beginning, the early first 3 minutes of the life of the universe. Okay, the next thing that occurred early on in the first 3 minutes is that the quarks, these were the fundamental particles I mentioned a moment ago. The quarks were, it was so hot back then, remember the temperature, 10 to the 30 whatever degrees. It was so hot back then that the quarks were able to fuse together. And when you couple quarks, and the two relevant flavors that are parts of everyday life, when you fuse 3 of the quarks together, you make a proton. And oh, I'm sorry, U and D are up and down. Don't ask me why they named them up and down quarks, but so 2 up quarks and a down quark create protons. So the protons that exist in the universe were created in the first 3 minutes, and they were created from the quarks that came before them. And if you have 1 up and 2 down quarks, you create a neutron. So protons and neutrons are the two fundamental particles which go into making up the various elements like hydrogen and helium and lithium and iron and all the other elements are made up, the atoms are made up of protons and neutrons. And as you probably know, electrons, which came early on, orbit around. Okay, so let me just take you through the early fusion of particles. So once we had protons and neutrons, it was so hot that the protons and neutrons, and that's what the laser fusion, by the way, at Lawrence Livermore does, makes it really hot and gives them enough energy to slam together and stick. Okay, well, back in the early universe, the particles, protons and neutrons, were fused together. And so for the first 3 minutes, we had hydrogen, one proton is a hydrogen nucleus. And it, on the left-hand image down there, fused with a neutron, proton plus neutron, slammed together, stick together, held together by the strong force. And they then, that's still hydrogen because this number of protons determines whatever the element is. Okay. And another event that occurred in the first 3 minutes is that sometimes a proton or a hydrogen atom would fuse, and this is the middle picture, with another hydrogen atom, and that would create helium. So helium is all the elements in the universe with 2 protons. Sometimes 1 neutron, sometimes 2 neutrons, but if it has 2 protons, it is helium. So we're early in the 3 minutes into the universe's life, and we've created some hydrogen, some helium, and the third one on the right is even more helium. Okay. And the so what about that is, that's it. There were traces of lithium, the third element, 3 protons that were created. But in the first 3 minutes of the life of the universe, the iron, the carbon, the lead, whatever else, still did not exist. Okay, so the first 3 minutes of the universe was leading us to hydrogen and helium. That's it. 75% hydrogen, 25% helium. That was all there was in the universe as far as matter was concerned. This fusion process I've just described to you, as I mentioned earlier, gives off energy. And some of the energy it gives off are the neutrinos. Those are the particles coming through our body. But the other thing, and this is incredibly important, the other thing that's given off are photons, electromagnetic radiation. Photons, just a word for the particles that are electromagnetic radiation. And the kinds of radiation, electromagnetic radiation that we talk about are the gamma rays, X-rays, ultraviolet, visible light, microwaves, and radio waves. And they're all electromagnetic radiation. The difference between all of them, these are literally particles that have waves inside them, and they travel at the speed of light. And the difference between all of these kinds of electromagnetic radiation is just the wavelength. If the wavelength is very short wavelength, then it's a gamma ray or X-ray. If the wavelength is very long, it's a radio wave. So the different kinds of electromagnetic radiation are just particles with wave properties of different wavelengths. Okay. All right, so that was 3 minutes into the life of the universe. Hydrogen, helium, electromagnetic radiation, it's really hot. And that was it. Oh, so we're not there yet. Okay, so this diagram takes you through time events. And of course, the Big Bang is what we started with. And for the first 1,000,000 years or so, the electromagnetic radiation created in the first 3 minutes was just seething throughout the universe. It was very, very hot. And as time went on, the universe expanded, but still no heavy elements. The heavy elements started to occur about 100 million years into the life of the universe. The universe was expanding, and as I said before, it was cooling down. And the gases that were created, the hydrogen and helium, the gases that were created were too hot to do anything until about 100 million years into the life of the universe, at which time the temperature was sufficiently low that clumps of gas could start existing. And those clumps of gas, how do they stay together? Gravity. Clumps of gas held together by gravity came into existence for the first time about 100 million years into the life of the universe. Okay? Still no stars yet. And that was the next step. The next step was the formation of stars. A clump of gas that was held together by its own gravity sometimes will be pulled in on itself. And that pulling in on itself creates stars. So stars are created even today when gases in space are sufficiently dense that their own gravity causes them, the clumps, to collapse. They form stars. And so the first stars are about 100 million years into the life of the universe. And this is a diagram I made showing the sun as a typical star. Gravity is holding it all together, and gravity is compressing it. And you probably all know what happens when you compress a gas. You compress a gas and it heats up, okay? In stars, the gas that is at the center, the hydrogen and helium that's at the center, is heated up enough so that the atoms in the center can then start slamming together because they're hot enough and sticking. And so the next development of elements in the universe occurred when stars started forming, like the sun. And they fused together particles in the center, the center of the stars. And then these arrows and circles are just, remember I mentioned that whenever you have fusion, you have energy given off as electromagnetic radiation. Those wiggly lines and stuff represent electromagnetic radiation coming out from the center of these stars. And that process of the energy, the electromagnetic radiation coming out from the center, that's why stars shine. So the energy that makes stars shine is created in the center. And it takes millions of years typically, but it takes time for the energy to get to the surface, fly away into space, and that's the starlight. Okay? So this process, and also, of course, the neutrinos, but we've talked about that already. Okay, so the first thing that happened was the core of the stars. The hydrogen in the core was mostly hydrogen, remember, was fused together to create helium. And eventually the cores of these stars, the first generation stars, were all helium. It turns out that when that happens, fusion stops. The star it still has its own gravity, but helium is harder to fuse. It takes more energy. It has to be hotter, or the helium won't fuse. So the helium cores of these stars then started contracting due to the gravity. Sorry about that. Due to the gravity of the starlight, the star gas around it, the core was contracting, the helium core, but not fusing, but getting hotter because it was being compressed. At the same time, as you can see, then a shell of hydrogen surrounding the core got hot enough to fuse into helium. And then helium ignited. And the helium cores started fusing into carbon and oxygen. And the carbon and oxygen cores, the core was eventually all carbon and oxygen. This is happening in the sun, by the way. It was all carbon and oxygen, and fusion stopped there. And then it shrank due to gravity. And then there were two layers of fusion around it. A shell of hydrogen was made hot enough to fuse outside the core. And between the hydrogen shell and the core, the helium that had been created there also started fusing into carbon and oxygen. And what happens is that the stuff that's outside the core is far enough away from the center so that when those two shells, the hydrogen fusion shell and the helium fusion shell, were going strong, they created enough photons, enough energy to literally blast the outer layers of the star into space. That event is called a planetary nebula. It's the fate of the sun, not in our lifetime, fortunately. Another 4.5 billion years to go. But I don't know if any of you know Charlie Sawyer in Pembroke. He took this picture of the Ring Nebula, shared it with me. This is a planetary nebula, a star that is blown up. Here's another one. Just there are lots and lots of them, and they have lots of different properties. Okay, as I said, there were new elements created in this process. And the elements that are blown into space by the planetary nebula: hydrogen, helium, carbon, nitrogen, neon, and sulfur. So many of the elements, many of those elements in our bodies on the Earth were created early in the life of the universe, but not at the beginning. Okay, but we still don't have iron or lead. That's yet to come. Okay, so the process of clumping together of gases to form stars, it turns out that the gases that were the early universe were sufficiently clumpy that large groups of gas were held together, and in these large groups of gas, many stars formed. Okay, and the many stars forming together, held together by gravity, are what we call galaxies. So a galaxy is groups of millions or billions of stars that are held together. In this particular case, the Andromeda galaxy is a bright one in the center. And stars continue to form in it even as we speak. Okay. It then turned out that the clumpiness of galaxies was not the biggest clumps in the universe. Clumps or groups of galaxies clumped together. And they created what are called groups of galaxies or clusters of galaxies. And I apologize, this picture isn't crystal clear, but there we are, surrounded by smaller galaxies. And another group of galaxies with us is surrounding the Andromeda galaxy. And turns out that the Andromeda galaxy and our galaxy are gravitationally held together. They're going to collide someday. So not in our lifetime. That's good news. And it turns out on top of that, that the clusters of galaxies are clustered together. The biggest clustering groupings of objects in the universe are clusters of galaxies called superclusters. So a supercluster can have millions of galaxies in it, all orbiting together. I'm just giving you the big picture of the universe so you know from whence we came. Just another picture of that. And this is a neat one. Each of these bright areas are superclusters of galaxies creating millions of stars every day. Okay, so this process is ongoing. Okay, once the galaxies formed, the gases in them were sufficiently held together by the gravity of the stars that other stars formed in the galaxies. And the stars that form later on, some of them, and it happens today too, some of them are much more massive, have much more matter in them than stars like the sun. Stars like the sun, as I told you, only created a few stars, a few elements by fusion. The rest of the elements in our bodies and on the earth are created in these supergiant stars. Same concept, gravity compresses the center, hydrogen fuses to helium, it collapses a little bit, helium fuses into carbon and oxygen, and then shells of other stuff are fusing around them. But with supergiant stars, there's enough gravity to hold it together to prevent the planetary nebula, okay? So that many shells, and you can see the shells I've listed there, of various elements being formed in the star while it is shining, okay? Well, eventually, the core of the star is converted into iron, okay? And iron, it turns out, does not fuse well. And so what happens is that the iron is being compressed by the gravity of the surrounding stuff, and it eventually becomes unstable, which is to say that the iron particles then are forced to collapse together at almost the speed of light. And this occurs for stars between roughly 8 and 15 times the mass of our sun, okay? And what happens then is that the core of iron collapses due to the gravity pushing in on it. It gets smaller and smaller, but there's a repulsive force called the electron degeneracy pressure. There is a repulsive force that stops the collapse. And here's the neat part. The collapse occurs at almost the speed of light. It comes to a screeching halt because of this repulsive force of electrons getting too close together. They repel each other. And it literally, the core literally bounces at almost the speed of light. And that bouncing of the core, then the other layers are following it in, gravity is still doing its thing, but the core is then suddenly blasting outward with a huge amount of energy. And the energy pushing out on those shells of fusing stuff blow the entire star into space. And that process, well, iron is not the densest element in the universe, but the process of creating the other elements with more protons than iron has primarily takes place in the explosion, the supernova. And this is what a supernova looks like. The Crab Nebula is a star that is exploding. It was a supermassive star, and it is ejecting into space essentially all the elements that exist on Earth. Okay, Earth doesn't exist yet. The Earth doesn't exist yet, but the elements that we're made of are coming into existence. Okay. All right, this diagram, not really well focused, but anyways, it sums up what I've just been saying. The formation process of the elements that are matter. The orange ones on top are the hydrogen and helium created at the Big Bang. And then the other elements created in the small stars, carbon, nitrogen, oxygen, I mentioned them earlier, and all the other elements that exist are created in the supernova process. Okay, so now at least we finally have the elements that are the matter of which we're made. So then comes the question, well, what's next? Our solar system still didn't exist. So we got to find a way to create the solar system, to put all this stuff together so that we can be here. Okay. All right, which brings us to our very own galaxy, the Milky Way. Excuse me. This is a side view of the Milky Way galaxy. It is, looks like a flying saucer, and essentially it's a disk. And that disk is made of stars, gas, and the remnant stuff thrown out by the explosions, which we call dust. And those white blobs above and below it are groups of hundreds of thousands of stars that are orbiting with our Milky Way galaxy. Okay, but in fact, we are in the disk. So top view of the same disk shows at the very center of our galaxy, there is a black hole. Its gravity is pulling things around, and orbiting around the black hole, that yellow region, the stars are moving like that. Okay, we're not there. That's good news. And it's good news because when stars blow up, if they were blowing up nearby, it would just wipe out life on Earth. Those spiral structures are called spiral arms. And the spiral arms of galaxies, I'll talk about them more in just a minute, are the places where stars are being formed today. And you'll see how in a moment. We are not there. We are not in the spiral arms. We are between two spiral arms right here. Okay. So our solar system, let me define the solar system. The sun and everything that orbits it is our solar system. Okay, that's the definition. And the formation process of stars, like the sun, occurs in one of two ways. This was actually first demonstrated to me by some European scientists. You've heard of record players? Okay. So imagine a record player. You take the pin out of the center and you put on the record player a dish. And you put the dish on, fill it with water. And then you turn the record player on to the slowest speed so the water doesn't fly away. You turn the record player on, and you have the water is the dish with the water in it is moving around. Okay, and you let it just get into what we call equilibrium. So it's just sort of smoothed out water. And then you take a pebble and you drop it into the water. And this was an experiment that was done. So it's not just hypothetical. What happens is that when you drop it in, ripples start being created where the pebble splashes into the water. But the fact that it's rotating causes those ripples to become spiral like that. And what happens then is that the gases in the galaxy, they are not moving at the same speed as the ripples. The gases move faster than the ripples. And so what happens is that the gases, think water here, the gases move through the ripples. These ripples in astronomy, these ripples are places, we call them spiral density waves, by the way, are places where the gases in the disk of the galaxy are denser. So as the gases come in to the spiral arm, passing through this region of denser gas, the incoming gas can be forced to collapse and form new stars. So in the spiral arms, the spiral density waves, new stars are being formed. That's one of the two mechanisms for forming stars, forcing the gases to clump together as they travel through the spiral density waves. The other method is that, remember I said the stars explode, supernovas and planetary nebulas and so on. The gases ejected by those explosions. Sometimes from far, far away, sometimes collide. And the colliding gases slamming into each other cause them to slow down, and they can clump together. And this is showing two regions of gas that are colliding, clumping together, and forming new stars. Okay, so those are the two major ways that new stars are formed. I don't know if you can, the picture is a little blurry. This is the Orion Nebula, the Orion molecular, the Orion constellation. Two shoulders, the 2 feet, the belt, 3 stars in the belt. And here, this region here is called the Sword of Orion. Now, if any of you have ever been in the military, I can assure you it's not a good idea to have a sword hanging between your legs. It's a very bad thing. But they decided to call that the Sword of Orion. If you go out some night when it's clear, find the Sword of Orion, that's where new stars are forming. Okay. And of course, with a telescope or binoculars, you can see more of the detail of the gases like you can see here. Another group of stars that has recently formed is the Pleiades. You can find that on a star chart, and you can see that. And you can see that these stars are surrounded by gas because the clumping gases have more gas surrounding them. And when the clumps get hot enough, the gases that haven't reached the clump, the young star, are blown away by the heat created by the young stars. That's what you see here in the blue surrounding the young stars.
If a star forms an arm, does it then stay in the arm, or is it ever leaving the arm?
Great question. If a star forms in the arm, does it stay in the arm, or is it ever leaving the arm? Remember that the gas that came in was moving typically twice as fast as the spiral arm itself. The stars that are formed, they continue to move at the same speed as the gas. So they'll go through the spiral arm, come out the other end. Yeah, great question. Okay, so we've gone in round numbers through the first 10 billion years of the life of the universe without the solar system. The solar system came into existence about 4.6 billion years ago. Okay, the universe roughly 13.7 billion years old. So for the first, roughly 10 billion years, 10 billion years, we weren't here at all. Okay, and then this is the process through which the solar system formed, which is what I was asked to talk about. From the upper left, gases from previous generations of stars collide. We believe that this process of forming the solar system was not an isolated thing. We believe that the sun and its orbiting stuff was formed with other stars, like the Pleiades. We don't know which of the stars were our birth childs. But I believe some astronomers are looking for the other stars, like the Pleiades stars. And they can find them by the chemistry. The chemistry of different stars is different. Okay, so first of all, you had this cloud of gas and dust, and it had the gas that is going to become the solar system. This gas, when it was clumped together, it had a small amount of rotation, which is to say it wasn't going straight in on itself. It was an irregular event, this collision, and therefore there was a very small amount of rotation. Would have taken this clump of gas millions of years to rotate once. But think about an ice skater doing a performance skating, and what she'll often do at the very end, okay, is put both arms out, I can't do this, put one foot out and give herself a twist. Okay? And once she starts spinning, not very fast, then she starts bringing everything in close like that. And that process, something called conservation of angular momentum, that process forces her body to speed up. The rotation increases when you bring the matter in close to the axis of rotation. And that is what happened to begin the formation process of the solar system. The material started, the debris started spinning faster and faster. And the process of spinning faster and faster caused it to form a disk. There's a bulge in the center, that's where the sun is going to be. But it basically formed a disk as it was clumping and spinning faster and faster. Spinning faster and faster. Sorry about that. Okay. The next step, the first step in the formation of objects was the sun. The sun formed first. And it formed first because the gravity in the center was greatest and pulled that debris in to form the sun. And you saw the picture of the sun shining earlier on. Okay. And that process of forming the sun stopped when the sun became so hot that it pushed the other gases that were following it in, it pushed them out of the way. So the sun formed, it started shining brightly enough to stop other gases from coming in. And in the upper right here, there were regions of, remember, lots of debris. All the elements that we've talked about were created earlier, and they're orbiting with the sun. And we're still working out the details, but it appears that the planet Jupiter formed first because it had a clump of material that was very massive compared to the other planets. So this clump of massive stuff condensed to form Jupiter. And Jupiter was orbiting around with this other debris that you see up there. And the gravity of Jupiter interacting with the other debris caused Jupiter's orbit to change and caused the debris to also start clumping together. So the formation process for the other stars, as I say, still a work in progress, okay, took place over millions, probably tens of millions of years as the disk became clumpier and planet-rich, 8 planets today. And the other debris that was sort of held in orbit, if you will, by the sun and guided by Jupiter, formed other things, smaller planets, dwarf planets. There were other bodies that formed that aren't here today. There were probably many bodies, large bodies, Earth, maybe Earth size or smaller, moon size, that collided with each other. And the collisions caused a huge amount of rocky stuff, the stuff we're made of, to spread out. So there's also debris in orbit around the sun, as well as the planets, and then the smaller planets is also debris. Asteroids, meteoroids, comets. Comets are rock and ice. Asteroids and meteoroids are rock and metal, just by the way, okay? And eventually then, about 4.6 billion with a B years ago, the solar system, with all of its elements and rich varieties that allow life to exist, came into existence. And I want to end with a quote from Joni Mitchell. I'll say it for the people who are, we are stardust. This was at, where did she do this? Was it at, I think so. I think it was at Woodstock. We are golden. I can't sing, so I'm not going to try. And we've got to get ourselves back to the garden. Thank you very much. Are there any further questions? I'd be happy to. Yes, please.
You started talking about how the early universe, the primordial universe was cooling down. I'm sure there are people who project where the universe is going to go into the distant future. Will it eventually reach zero K? Is that the theoretical limit?
Oh, great question. Okay, so the universe is expanding. The energy that was created at the Big Bang is being spread out. It's like an oven. Turn the oven off, open it up, the heat comes out. Same thing with the universe. It's cooling off. And so the question is, will it ever get down to zero, no temperature? Okay. And the short answer is yes. And the reason, this has only been discovered in the last 20 years-ish. The reason is the universe is expanding because of the explosion, okay? Back in the olden days, 20, 30 years ago, back in the olden days, astronomers, astrophysicists believed that the gravity of all the stuff in the universe was sufficient to someday stop its expansion. This gravity over here pulling on this stuff over here, stop the expansion, and then it would recollapse and maybe have another Big Bang. Okay, well, it was recently discovered that there is a fifth force in nature, and it's called dark energy. And what dark energy is anti-gravity. So dark energy is causing all the universe to expand faster and faster. And so the universe is getting bigger, faster, and that process will continue. And eventually, whatever that means, trillions and trillions of years in the future, perhaps, the temperature will have fallen, gotten closer and closer to zero. And unless there's something else that we still don't know about, it won't stop approaching zero. Does that answer your question?
Yes, but I have another question.
Good.
What happens inside a black hole?
Oh, well, a black hole is a region of space where the matter in it has become so dense that it literally changes the shape of the space. And that the matter that was maybe a part of a star then collapses, and it becomes mathematically what we call a singularity. It is a region where the shape of space is completely distorted. And as a result of that distortion of the shape of space due to the incredibly dense matter, it turns out that nothing can escape from that region. If you fall into here's a funny thing, if you fall into the black hole, which you don't want to do, you'll be pulled, if you go in feet first, gravity acting on your feet will pull you faster than the gravity up here. So you'll be pulled out long, okay? But assuming you can survive that, you'll fall into the black hole and you'll go down and then become part of the singularity. But the neat thing is that if I watch, I'm not going to go in the black hole, but if I watch somebody going into a black hole, what I see from far away, because of the nature of nature, what I see far away is that person or object falling towards the black hole, being stretched out and coming to a screeching halt just outside the boundary, which is called the Schwarzschild radius, by the way. As seen from far away, time slows down as you approach a black hole and comes to a complete stop at the boundary. So I would see that object or person last forever. Am I answering your question at all?
Well, I guess misguided because I thought it would be incredibly dense inside a black hole.
No, it's empty space except for either if the material that made the black hole was not spinning, all of that material that is the singularity is a point at the center. How big? Smaller than we can measure. If it was a spinning object that condensed to become the black hole, the singularity is a ring inside the black hole of infinite density. And I mean, that's where the science fiction comes in, is that they hypothesize if you could fall into a rotating black hole called a Kerr black hole, And don't hit the singularity, but go through the middle. The science fiction is you could come out the other end. But there's no mathematical,
Is that point of infinite density real then?
it's real.
So it must have incredible temperature.
Well, that's just it. The problem with assigning it a temperature is it's infinitely small. Great questions, thank you. Any other questions? Or from our listeners abroad?
I don't see any questions coming through on the
That's-
chat yet.
That's fine. Okay, well, thank you once again for coming.